All right, let's talk about how machines actually learn. We're going to start with a problem you deal with every single day, and we'll end up at the core building blocks that power basically all of modern AI. Let's dive in. So it all starts with a simple question. You open up your inbox, and somehow it's already filtered out all the junk. I mean, there isn't a person sitting there reading your emails, right? It's a machine that has learned to tell the difference. But how? Well, this gets us to our first big idea, classification. At its very heart, that spam filter is a classifier. Its job is to look at every single email that comes in and make a really simple, educated guess. Is this spam or is it not? This fundamental act of sorting information into different boxes, well, that's a cornerstone of machine learning. One of the classic tools for a job like this is the naive Bayes classifier. It's a really clever algorithm that uses probability to make its guesses. Now, the most important word on the slide, by far, is naive. The classifier makes this one huge simplifying assumption. It assumes that every single word in an email is completely independent of every other word. So, for example, it thinks the word free has absolutely no connection to the word money. You know, that naive assumption, it's both its greatest strength and its biggest weakness. It makes the classifier incredibly fast and simple to run, which is perfect for sorting massive amounts of text, like in a spam filter. But the downside is huge. It literally can't learn that some words go together, and it can get totally thrown off if it sees a word it's never encountered before. Okay, so we've got the idea for a classifier, but how do we actually teach it to be any good? It's not magic. It's a very methodical process of training and then testing. You can think of it just like teaching a student. You give them the textbook, and then you give them a final exam to see what they actually retained.
A super common way to do this is called the holdout method. You take all of your data, let's say thousands of emails that you've already marked as spam or not spam, and you split it up. The bigger chunk, maybe 80%, that's your training set. That's the textbook the model studies to find patterns. The other 20%, you hide that away. That's the testing set, the final exam full of questions the model has never, ever seen before.
So, how do we grade this final exam? We use something called a confusion matrix. A true positive is a home run. It correctly identified a spam email. Perfect. But a false positive, that's the one that drives you crazy. That's when an important email gets thrown in the junk folder. And a false negative is when a piece of spam actually makes it into your main inbox. By counting all of these, we get a really clear report card on how well our classifier is doing.
Sorting emails by looking at one word at a time is one thing, but what about recognizing a cat in a photo, or understanding what someone is saying, or driving a car? The real world isn't just a simple collection of independent words. It's packed with complex relationships and context and patterns. A simple classifier just can't keep up. For that, we need to bring out the big guns: neural networks. And this is where we get into the world of neural networks, these big, complex systems inspired by the brain with layers and layers of interconnected nodes. But what is it that actually makes a deep network with tons of layers so much more powerful than a simple one? Well, the secret isn't really in the layers themselves. It's in this tiny, crucial component you can think of as a hidden switch. Let's do a little thought experiment. Imagine we build a huge, deep network, 10 layers, maybe even 100 layers of calculations, but we leave out this one special ingredient, this little switch called an activation function. What happens to our big, powerful, complex system? It just collapses. Without that switch, all the math in that deep, complex network just simplifies itself right back down. All those layers effectively merge into a single one. And suddenly, you're left with a system that's no more powerful than the spam filter we started with. All of that amazing potential is just gone.
So how do we stop that collapse from happening? Well, we have to intentionally add something that acts like brakes or maybe speed bumps into the system right after each layer. And that is the entire job of an activation function, to add a tiny dose of what's called nonlinearity, which is just what stops all the layers from blending together. The source material uses this fantastic analogy. An activation function is like a speed bump. It breaks up a straight linear road and forces a moment of change. In a neural network, it does the exact same thing. It breaks that simple chain of math, which is what preserves the depth and the complexity of the whole network. So in practice, at every single layer of the network, this little two-step dance just repeats over and over again. First, the data gets transformed by a matrix of weights. Think of those as dials that turn the importance of different inputs up or down. Then, that little activation function, that switch, gets applied to the result before it's passed on to the very next layer.
Now, as it turns out, there isn't just one kind of switch. Researchers have come up with a whole bunch of different activation functions over the years, and each one has its own little quirks and is good for different things. So let's go on a quick tour and meet the main players. We're going to focus on the three that you're going to see almost everywhere. There's Sigmoid, which is kind of the original. Then there's Tanh, a slightly better version. And finally, ReLU, which has pretty much become the champion for most things today. First up, the old school classic, Sigmoid. For a long time, this was the standard. It does one thing really well. It takes any number you give it, positive or negative, and it neatly squashes it into a value between 0 and 1. This is awesome when you need an output that acts like a probability. But for really deep networks, it has a major flaw. It can slow down the learning process to a crawl. So next, we have Tanh. It works a lot like Sigmoid, but instead of 0 to 1, it squashes numbers into a range between -1 and 1. Now, that might seem like a tiny change, but having the output centered around 0 actually helps the network learn much more efficiently. For that reason alone, it's almost always a better choice than Sigmoid. And that brings us to the current star of the show, ReLU. That stands for Rectified Linear Unit, and its rule is just beautifully simple. If a number is negative, the output is 0. End of story. If the number is positive, the output is just the number itself. That's it. And that incredible simplicity, that's its superpower. As the source material makes perfectly clear, ReLU is the go-to choice now for a very simple reason. It just works better. In most situations, it helps networks train faster and get more accurate results. It's the default starting point for almost everyone these days. The advantages of ReLU are just huge. It's incredibly fast to calculate, and it helps networks learn much quicker. But it does have one famous weakness, known as the dying ReLU problem. It's possible for one of the neurons in the network to get stuck always outputting 0. And at that point, it basically dies and just stops learning anything new. It's a risk, but it's a risk that's often well worth the trade-off. So let's just pull back for a second. We started with a pretty simple spam filter that just looked at words one by one. We saw that to tackle harder problems, we need networks with real depth. And we found that the secret key to unlocking all that power wasn't something complicated. It was a simple, nonlinear switch that keeps the entire system from collapsing on itself.
And that's really the powerful idea here, isn't it? The fact that so much incredible complexity can emerge from such a simple rule, a switch that's just on or off, a little nonlinear speed bump. It just leaves us with this final question. As AI gets more and more advanced, what other elegantly simple principles like this are just waiting out there to be discovered? Thanks for joining me on this explainer.
So where's this from? It's all coming from the channel Learn with Praveen.